What can be most frustrating for students is looking at a given reaction and deciding whether or not the major product is going to be from a substitution reaction or an elimination reaction. So in this video, what we're going to talk about is how we evaluate all the different factors in a given reaction to decide which pathway is going to be the major one. So let's look at two different reactions. Here you have tert-butyl iodide with sodium methoxide. Notice that the major product here is from elimination. So the elimination is the only product that we observe. However, if we have water, if we dissolve tert-butyl iodide in water, what we see is that the major product is actually that of substitution. So in this case, elimination predominates. In this case, substitution predominates. So we need to understand why those two things happen. A hint would be to look at the nature of the nucleophile or the base in each case. And sodium methoxide is a strong base, and so in that case it's going to act like a base, and elimination is going to be favored. In this case, water is a very weak base, so it's not going to abstract a proton. It's going to act as a nucleophile, and that's why substitution is preferential. Let's look at another example. So let's say we compare this reaction that we just talked about where elimination is a major pathway. So here we have elimination being favored, but notice if we use the same conditions but we have a primary alkyl iodide instead of a tertiary one, now substitution from an SN2 pathway is major. So why would that be? Well, remember that as we increase the substitution, we favor elimination, right? Because substitution happens by attack at the carbon bearing the leaving group. This one is less hindered than this, so now substitution can outcompete elimination. So let's look at some factors that we can use to generalize these observations. We can break reagents up into four categories, and really I'm only going to be concerned with three of those four categories. So we can have something that acts only as a nucleophile. So these are not good bases. So these are weak bases, good nucleophile. These would be the halides, anything containing sulfur. So these are weak bases, but they're very good nucleophiles. So one would imagine that these favor substitution. So substitution would be favored in these cases. We're not really going to worry about these. These will only act as a base and not a nucleophile. Here's some of those examples, but let's not worry too much about those. Let's skip this category and go over here. Water, methanol, ethanol. These are weak nucleophiles and weak bases, but these tend to also favor substitution, but from an SN1 pathway. These can do SN2 or SN1 depending on the nature of the substrate. And these can also do SN2 or E2 depending on the nature of the substrate. These are strong bases because they have a negative charge on the oxygen, and strong nucleophiles. So depending on how substituted your substrate is, that's going to determine whether or not you're going to see elimination or substitution. Unhindered substrates will give you substitution. Hindered substrates will give you elimination. Okay, so let's look at some examples. So here we have a primary electrophile, a secondary electrophile, and a tertiary electrophile. Br minus is in the category of nucleophile only. So it's a weak base, but since it's large and polarizable, it's a good nucleophile. Since this is primary, we're going to expect this to undergo SN2 substitution. Since this is secondary, we'll expect this to undergo SN2 substitution. But tertiary, so this would be a minor pathway, so I'm not going to ask you to worry about that. But for tertiary, that can't undergo SN2, so now SN1 will be the major pathway. But whenever you see sodium bromide, you want to think substitution. It could be SN2, it could be SN1, but it's not going to be elimination because it's not a strong enough base to carry out a proton transfer reaction. Okay, so what about these cases? Again, we have primary, secondary, tertiary, right? So in the first case, primary, we could think that that would either undergo SN2 or E2, but since this is both a weak base and a weak nucleophile, this would be no reaction, right? And actually it turns out in the case of secondary substrates, these also are no reactions. So not practical means that in a reasonable period of time, these reactions won't occur. But in the case of a tertiary substrate, you're going to get a mixture of SN1 and E1. But remember, E1 is always a minor byproduct of the SN1 pathway. So we expect SN1 to be the dominant pathway. So these, whenever you see water or any alcohol, methanol, ethanol, you want to think SN1. And that's only by this pathway. In these two cases, that would be no reaction. The only time that you're going to see E1 as a major pathway is when you have an alcohol and a non-nucleophilic strong acid. So H2SO4, for example, or H3PO4. Okay, so let's look at these cases. Now if we have hydroxide or some other alkoxide, right, it's both a strong nucleophile and a strong base, so now we might expect, because it's a strong base, to see elimination. In the case of the primary, since it's not hindered, SN2 is a major pathway. But as we increase the substitution at this carbon, as we bond that carbon to more carbons, the elimination pathway becomes the major one. And so this reaction pathway would favor SN2 reaction to give an alcohol here, but this one would favor E2, and this one would also favor E2. So as we increase the substitution with something that's both a good nucleophile and a strong base, as we increase the substitution from primary to secondary to tertiary, then we increase the likelihood that we'll see elimination. Okay, what about this case? So notice that now what we're doing is we still have a primary substrate. We have a strong base. So in the previous slide I said that would favor substitution, but notice that in this case E2 is a major pathway. So the only exception to that rule is if you have a hindered base, that is going to favor elimination, even if you have a primary substrate. So a hindered base, like potassium terbutoxide, is going to give the E2 product even if you start with a primary substrate. So let's summarize all these rules in some kind of system that's much easier to understand. When you're trying to decide between substitution or elimination, really you just want to be able to evaluate 3 different factors, and 2 out of 3 of those factors favoring either substitution or elimination is going to give us whatever answer, right? So factor 1 is the strength of the base. If you have a weak base, that's going to be a water, an alcohol, a halide, anything with sulfur, azide, cyanide, or carboxylate, that's going to favor substitution. These are not strong bases, so substitution is going to be favored in those cases. But anything with a negative charge that's not resonance stabilized on oxygen or nitrogen, these are going to be strong bases, which are going to favor elimination. Then you go to the second factor, right? You look at the hindrance of your base, or sorry, you look at the hindrance of your substrate, right? So if your substrate is primary, that's going to favor substitution, right? Because this carbon is not very hindered. But as you get to secondary or tertiary substrates, that's going to favor elimination, right? Because now it's much more difficult for the nucleophile to get into this carbon. It's easier to just pluck off a hydrogen on the outside and do elimination chemistry. And then the last thing you want to look at is how hindered the base is. So pretty much all bases, we're going to say all bases are unhindered except for 2. That's either going to be tert-butoxide or LDA, which is diisopropyl amide, which is a negative charge on this nitrogen flanked by 2 isopropyl groups. So these are the only 2 examples of hindered bases. If you see these, you want to think elimination. If you see these, you want to think that could possibly favor substitution. So 2 out of 3 wins, right? So let's go back to some of the examples that I just gave, right? If we look at this, if we're trying to evaluate each one of these factors, right? We look at our base, right? We have a negative charge on oxygen. That's a strong base. So that's going to favor, since it's a strong base, that favors elimination, right? We look at our substrate, it's primary, that favors substitution. So the tiebreaker is the hindrance of our base. This is one of the two hindered bases that we talked about. So yes, that favors elimination. So we have two factors favoring elimination. That's why elimination is the major pathway. But if we go back one slide, right, with sodium hydroxide, we have a primary substrate. So that favors substitution. We have a strong base. That favors elimination, but it's not hindered. So that favors substitution. So now we have two factors favoring substitution. So the SN2 product is major, which would look like this. So that's how you decide between substitution or elimination. So to summarize the chapter, right, you want to know the trends for each type of reaction. You want to be able to evaluate your electrophile or your substrate, right? Is it primary, secondary, or tertiary? More substitution is going to favor elimination. You want to look at your nucleophile. Is it a good nucleophile or is it a bad nucleophile? Is it a strong base or is it a weak base? Do you have a good leaving group or do you have a poor leaving group? Be able to draw potential energy diagrams for all the reactions that we talked about and be able to write a rate law for each reaction. Be able to use curved arrows to depict all these different mechanisms and know how the stereochemistry is affected, meaning that you get a mixture of stereoalkene isomers from E1 reaction, but E2 is stereospecific and you have to have an anti-coplanar arrangement of the hydrogen and the leaving group. And most importantly, you want to be able to predict the major products for each reaction and know what kind of mechanism it's going to take place under, whether that's SN2, SN1, E2, or E1.